Alex Martelli right now with exception and error handling in Python 2 and Python 3. Thanks.
Hi. Can everybody? Can everybody hear me? Is it on? Okay, great. So I'm surprised to have this introduced as an interesting subject. It is, of course, but I actually deliberately picked something that is hardly exciting. It's not like one of the big things. Ooh, I can handle exceptions better. It is important because exceptions are with us all the time. And specifically, this talk is a highly condensed version of Chapter 5 of the 3rd edition of Python in a nutshell, which is available in early release ebook version only for now, but you can pre-order the paper book. Using this URL, you can get a 50% discount on the ebook, only 40% on the pre-order of the paper book. The point of getting the early release, it's raw and unedited. It's the early version. You get a chance to help the Python community, and as in particular, by sending us feedback, comments, pull requests, well, not really, but the equivalent, so we can make the book the best we can to serve the Python community. So please take advantage of this. I'm not sure how long the offer will stay on. That depends on our editors at O'Reilly, but definitely it will be on throughout the conference and probably a few days later. So since I do mention the book from which this whole chapter is taken, I cannot fail to mention my co-author who have been nice enough to join me here, Anna Ravenscroft and Steve Holden. Besides the holy bond of marriage between me and Anna, what joins the three of us is we're each of us a PSF fellow. In fact, Steve actually founded the PSF back in the day. And each of us separately won the Frank Willison Memorial Award for contributions to the Python community. These are our modest credentials. I think we're doing the best job we can in the 3rd edition of Python in a nutshell, covering both Python 2.7 and Python 3.5, including how to transition between them, how to have them coexist, and various strategies you can adopt. And this is a sample of it, the focus on exceptions and errors. I do feel the need to distinguish because in Python, and that's a crucial step towards understanding and learning Python for anybody coming from just about any other languages, exceptions are not always errors. They can be. You try 1 divided by 0, it's an error. You cannot divide anything by 0. So you get an exception, 0 division error. The error in the name of the type of the exception tells you, hey, there's a mistake, there's an error. But there are things that are not errors at all, yet cause an exception. Take, for example, any iteration. In this case, I've taken an empty list, but it need not have been empty. I called iter on it to make an iterator. And now I'm trying to get the next item. There are no more. It's empty. There are no items. That's not an error. It's perfectly normal. Indeed, what happens when you call next here, you get a stop iteration exception. Note, it's not a iteration error. There is nothing wrong with the fact that an iteration finishes at some point. Now, this one finishes very early because we start with an empty, but every iteration had better finish eventually, right? So when I say exception, I don't necessarily mean error. This is obvious to anybody who's used Python for a while, but it needs to be repeated because I'm trying in this note to address people who are new to Python. They may be very strong programmers in one or two other languages, but this is a peculiarity of Python. Don't fear exceptions. They don't necessarily mean errors for you. Doing well? Better? Okay. So, to handle exception, the key tool is the try statement. It's got somewhat rich and complicated syntax, but you always try a block of code, then optionally have 0 or more except clauses, where essentially you're telling Python that you're expecting one of these type of exception may be caused, and you may have an as something subclause to get the exception object. The crucial thing here, which keeps catching people, including reasonably experienced ones, the except clauses need to go from narrow to broad. They are conceptually tried in exactly the order you specify. So if you have something like except exception or except colon, that will catch everything. Every further except clauses you may have is completely ignored. That's an error which a tool like PyLint may be able to catch, but may not, so be very careful. Always narrow to broad. Incidentally, as we'll see, the logic is that of inheritance. So when you're catching a type, you're catching all of its subtypes, all of its subclasses as well. So it never makes sense to have an except one type, blah, 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 except a subtype. The second clause will never trigger, because if that subtype had happened, it would have been caught in the main one. A sadly neglected clause in try statements, which deserves much more use, and I'll harp onto that later, is the else clause. Maybe it's not very used because it doesn't come particularly natural. Else means if none of these exceptions has occurred, only if no exception at all has occurred in the try block, then continue doing this work without any exception guard. As I've joked in the past, except could almost as well be spelled expect. When you have an except clause, you're essentially telling Python and telling the reader of your program that you expect one of those exceptions might occur, and then you want to catch it and do something about it. So the code you put in the else, you are not expecting exceptions. And that's important, because if you get exceptions you didn't expect, then you don't want those unexpected exceptions to be caught by mistake. You want them to cause problems so you can debug your program. Finally, oh, by the way, you can only have an else if you have some except. Otherwise, it makes no sense. So there must be except clauses for you to have the optional else clause. And then, optionally again, the finally clause, which unconditionally executes at the end. Now, one peculiarity, which unfortunately we've carried over from Python 2 to Python 3, if you try to finally continue, Python will catch that for you as an error. Continue is not allowed in a finally clause. Think about the semantics of finally and continue. Really doesn't make much sense, wouldn't make much sense. However, break and return are allowed, and very counterintuitively swallow and clear any pending exception. Nobody expects that. I mean, I've just explained the rule, and yet if tomorrow I'm staring at a piece of production code which mysteriously makes an exception disappear, it will take me half an hour to spot, oh, there's a finally break or finally return. Of course, I know that swallows any pending exception. It's very counterintuitive, and Python has so few counterintuitive niches and corners that this is really worth spelling out. So make it a personal rule. Program your linter like PyLint or something to slap your wrist if you break it. Don't use break or return in a finally clause. Don't worry about erroneously using continue, because if you do that, Python itself will catch it as an error, but break and return are subtle. Again, semantically doesn't really make much sense. Finally break would mean, okay, so do all of this and then exit the loop. Well, just finish the loop right there, right? It's not, what's that break for? And the same goes for return. Now, try lets you handle exceptions that happen for whatever reason. For example, you have 1 divided by 0, you may have an except 0 division error to handle that case. But you also need a way to deliberately cause exceptions, make them happen, and that's the raise statement. In Python 3 exclusively, in Python 2 very recommendedly, the syntax is very simply raise some object. That object must be an exception object. It therefore must be an instance of base exception. Of course, as usual, when I say an instance of, I mean an instance of that class or any subclass. You never instantiate base exception directly. You're always going to instantiate subclasses thereof. In version 2, you could alternatively raise a class, which was a subclass of base exception. That always was a bad violation of one of base then of Python rules. There ought to be only one way to do something. And so every time I taught intermediate Python, people would ask me, so what's the difference between raise type error, comma, foo versus raise type error, open paren, foo, close paren? And I had to explain, there is absolutely no difference. So why do you offer me 2 ways? Whoops, now we don't anymore. In Python 3, you always instantiate the exception object and raise that. A very important form is raise without any parameter, just a bare raise. That re-raises the exception being handled. So therefore, it's only allowed if an exception is being handled, which means a bare raise without any argument can appear in an except clause, or it can appear in a function, which gets called from the except clause. Essentially, that lets you catch an exception, use an except clause, do something like record that problems occurred, save some state somewhere and so on, and then just say raise, so the exception keeps propagating and ends up giving some error message to the user and so on. But meanwhile, you've had a chance to do logging or cleanup or something, a very important idiom. So, given that Python is going to raise exceptions for you in many error and non-error cases, it seems natural to wonder, when should I be doing the raise? Apart from when you've got a very nice full house like that, in which case I would raise, but kind of depends on your poker style. For example, That's because you want to diagnose as an exception something that from Python's viewpoint would be perfectly legitimate, but it isn't within the semantic of your specific program. For example, I've coded a trivial cross product. Of course, you could do it with iter tools and do a better job, but if I didn't have the if statement, either sequence being empty results in the cross product being empty. That's the natural definition. Maybe in my particular application, it makes no sense to have an empty cross product, and I want to make sure that anomaly doesn't get overlooked. So I want to add one check to those Python implicitly performs for me. If either of the two arguments is empty, then I raise a value error. Remember, the general idea of value error is it looks like the type is right, but the specific value of this object isn't. So pass a different object of this type. In this case, an empty sequence is fine in terms of type, but it's not for my semantics. And then I just do the operation. A crucial point of best practice. This only tests and raises for stuff that Python would not object to, stuff that would pass happily Python's checks. For example, I don't check that sec1 and sec2 are iterable. If they aren't, that list comprehension will raise, presumably, a type error that will be perfectly fine. I don't duplicate Python's own checks. Not just wasted work, it makes your code more readable because the reader has to wonder, why is he doing this when Python obviously does it anyway? It'd be like saying, if y equals 0, raise zero division error, else return x divided by y. Why is he checking explicitly? Doesn't the obvious zero division error Python does work well enough? It usually does, and therefore be very careful not to duplicate error checks. Something that a raise, especially a re-raise, can often help you with is a v3 only feature, which is essentially exception wrapping. In v2, there's only one active exception at most, one exception being handled at any time. Separately and equally, there is a traceback that keeps track of the sequence of call frames, the stack of call frames that led to that exception. And the two are not really well connected. V3 is our jargon, since we're always needing to say Python 3.5 and Python 2.7 to make the nutshell a tiny little bit smaller. We've introduced the jargon V2, version 2, meaning specifically Python 2.7, and V3 meaning specifically Python 3.5. Just, it's, as I said, this is kind of the condensation of that chapter, so our convention kind of seeped through. In V3, the traceback is held by the exception object itself. It's one of the attributes of the exception object. An architecture that makes much more sense if you think about it. Every exception keeps track of the traceback that happens. So you can change the traceback using the withTraceback method of your exception object. That gives you a copy, but the traceback object changes. And also, when a new exception arises while another one was being dealt with, the new one doesn't trample over the old one entirely. The old one is remembered as the dunder context attribute of the new one. Incidentally, dunder is a normal way to pronounce the double underscore before and after, which is so common in Python in the magic names. Last but not least, if one exception causes another, you can now record the fact explicitly with the raise from statement. Earlier, when I documented raise, I only showed the two forms that apply in both V2 and V3. In V3, there is a third form, which is raise, some new exception, from something else. The something else can be none, to mean no cause in particular, or it can be an exception object which caused the current one. Let me give an example. I think that will be clear. So, for example, I have an inverse function in V3. Is a code readable? I had to put a lot of things on. I hope I didn't make it too small. Except in the case somebody asks me the inverse of 0, I want to make sure I raise a value error, because I consider the fact that inverse is obtained by dividing an implementation detail. The point is, a 0 argument has the right type but the wrong value, so it's a value error. However, I don't want to hide the fact that what caused me to recognize the value error is actually the 0 division. So, after this implementation, if I ask for inverse of 0, I get a complete diagnostic. First, the 0 division error gets shown, and then, and I've highlighted this, but it's text that Python itself in V3 produces for you. The above exception was a direct cause of the following exception, the one that actually happens, which is the value error. Note that when you use a try except, the exception you need to catch is the value error. The other one, the 0 division error, is not the exception being handled. It's already been handled here, and it's recorded, since you do a raise from, as the cause of the actual exception that propagates. So I think that's a much clearer way to handle more than one exception. An even more obvious case is the context. I mentioned it briefly. Suppose that's an overly simplified example, that you have a try something, handle an exception, and in the course of handling that exception, you cause another exception. In this case, I've done number plus string, which makes no sense in Python. In V2, if you do that, the new exception, the type error when due to mixing integer and string, tramples over the exception you were handling. So the fact that there was a 0 division error which produced all the fracas is kind of forgotten. That can make, I don't know if you've ever happened to you that you're chasing after an exception that's due to an error in a handler, which in turn completely hides the root cause, which is the exception that caused the handler to execute in the first place. In V3, thanks to the context, when this exception gets raised, Python sees that it was raised while another exception was being handled, so it records the exception being handled as the context for the exception that propagates. And if it reaches the except hook, the top level, what you get is the original diagnostic, the division by 0 that you quote here, and during, again, this is text from Python itself, during handling of the above exception, another exception occurred, and you get the complete diagnostic. Again, error shouldn't be suppressed unless, it shouldn't pass silently unless explicitly silenced. It's one of the core ideas of Python, and V3 is a better Python than V2 was, because it's not causing any pass silently. As an alternative to finally, you can use the with statement. You need a context manager here. This is my translation showing how much work with does for you. It relies on special method enter and exit, dunder enter, dunder exit. And this also illustrates some details that people may not have entirely clear. The exit is called with 3 nons if there has been no exception. It's called with the type, value, and traceback. For V2 compatibility, it needs all 3, which incidentally, you can always extract at any time with sys.exinfo. You'll get none, none, none if no exception is being handled. And if it can return a false value to cause a re-raise, so the exception propagates. But if it returns a true value, it means, okay, I've handled it, don't propagate. Has to, of course, you can code a class with dunder enter and dunder exit, but it's usually handier to use the context lib, context manager decorator, and write a simple generator. The yield is whatever gets obtained when you write with this stuff as x. X is assigned whatever you're yielded. And then for the exit and so on, you use an except and a finally. That's possibly a more natural, more Pythonic approach. Since I mentioned generators, albeit just in the context of using them to make context manager, one addition that's also in the last V2 is that whoever is driving a generator can now raise an exception inside the generator with the throw method. The throw method is much simpler in V3 because you just pass it an exception object, and that has all the information needed, including the traceback. In V2, you may need to explicitly pass the usual tripled type, value, traceback object. And within the generator, if you expect to be used that way, you do a try except and generator exit. Note again, as usual, it's not a generator exit error. It's not an error. It's a normal occurrence. It's the proper way generators get terminated from the outside, but they do need to handle the exception to do whatever cleanup they may need. I assume we all know that how exceptions propagate, but I thought a slide reminding of that is not out of place. It's a bubbling up. The stack of call frames get dismantled, bottom to colored to color to colors color and so on. At each level, an except clause or a with an exit in a context manager can catch it and say, okay, it stops propagating. As long as this doesn't happen, any finally clause or context manager exits on the way up execute as they get bubbled through. If it goes all the way to the top, then is where sys.accept hook, which I've shown only the default, but you can do all sort of custom handling, except what you can do is essentially reporting and logging. The whole state in the stack has been destroyed before sysaccept hook takes control, so it's too late to redo anything. And finally, if sysaccept hook accepts the program termination, that's when atexit triggers. Note that the finally closes and so on trigger on the way up, but the atexit functions trigger at the very exit when it's irretrievably terminating, when the program is irretrievably terminating. Right. So I mentioned briefly in the context of narrow versus broad except clauses that exceptions come in a hierarchy. Version 2 had, since I believe 2.4 or 2.5, tried to make it very precise with an exception level derived into a standard error, which has all the errors, and then non-errors, like stop iteration and warning, under exception, other non-errors, like generator exit, directly under base exception. The whole motivation for this, and other little details which I've highlighted here, such as having IO error and OS error separate but related by deriving them from environment error, was well-intentioned, but a few years of practice taught us to simplify most things and complicate another. So in V3, this is simpler overall. There's only the exception level. We've lost the standard error level. It doesn't really buy you anything. On the other hand, OS error has become a synonym of IO error and environment error. They're all names for the same class, but it spawned a lot of subclasses, such as file not found error is now a specific exception class. Why? Well, it's not indispensable. In V2, suppose you want a function that reads and returns the content of a file at a certain path. But if it can't read it, because the file isn't there, it returns a default value instead. Pretty normal. So in V2, you have to use a try except, trying to open and read, catch the IO error, make sure the IO error is specifically file not found. And yes, enoent, meaning file not found, may not be the most obvious abbreviation in the world. We have it from C and Unix, because otherwise you don't want to hide other errors. For example, if the file is present but you have permission problems, you don't want to hide that. It's only the absence of the file you want to trigger the default. So therefore, if the error number is not the specific one you care about, you re-raise the exception. Now, in V3, this has substantially simplified because you can catch specifically only the common important case that you want to handle. The file wasn't found. Any other IO error, so the file was found but you didn't have permission, or the disk is damaged, or whatever, you will propagate automatically. So as you see, the logic is substantially simplified. And this is not necessarily in this default thingy, but overall a very common requirement. Given how many exceptions there are, you may wonder, should I ever define custom exceptions, an exception all of my own? My answer is absolutely yes. I consider it a best practice if your module, package, library, whatever conceptual level is appropriate, defines a custom exception class, which I personally like to call error, assuming it's only used to diagnose error and not other non-error situations. Why? Because client code that exercises your package, uses your functionality, can easily catch any error specific to your package with a try your package.something except your package.error, whatever proper handling. But a trick that's often missed that I think also qualifies as a best practice is to use multiple inheritance. because many of the specific errors your package may want to raise as an exception have two key core characteristics. They are very much errors specific to your package, but they also may be errors that are obviously type errors. That is, you've been passed an argument of an inappropriate type, or they may be value errors. Type is right, but the specific value doesn't work. So how do you do both? Easy. You use multiple inheritance. I'm not going to say that's why Python has multiple inheritance. There are other uses, but this is one of the best. You define a class. I would call it my type error, but it didn't fit on the slide, so I called mighty, which inherits from both your package's error and the standard type error. So client code can, depending on the client code needs, can catch all type errors, whether generated by your package or otherwise, by a except type error. This will catch, since it uses the rules of inheritance, it will catch yours as well. Or it may catch all errors from your package, like above. So this half, well, a bit more than half of the talk concludes what I would call the tactics, the technical details of exception handling in V2 and V3. The rest of the talk I'd like to keep on a strategic, as in how do I handle potential errors and exceptions? How do I structure my code to handle them? I would, if you have any question about this part, I would ask you to jot them down so we can have all questions at the end. But if there's something really burning right now, this is a good break point, about halfway, almost halfway. Okay, let's keep 10 minutes for any question at the end. I hope the questions will actually be more on the strategies, because that's a much more interesting part. So, I apparently coined this particular contraposition, or put it in these terms. There are two big categories of strategies that you can use to be prepared about errors. One I called, using a common English proverb, look before you leap. LBYL is not really shorter, so, but it sounds acronymical and therefore more technical. And borrowing the sentence from Admiral Grace Murray Hopper, it's easier to ask forgiveness than permission. Look before you leap appears to be a very reasonable thing. Make sure all the prerequisites of whatever it is you actually want to do are satisfied. If any is not satisfied, either raise an exception or otherwise signal error and avoid the operation. If everything is satisfied, perform the operation and expect to see no problem, no exception. The alternative, I don't think this is quite what Admiral Hopper had in mind. Sure. Oh, okay. Was just try performing the operation. Try as in the try except. Let Python catch all the prerequisite violations. It's pretty good at that. Let it raise the exception, and you may want to catch it in order to add information, like we've seen in version 3, the root cause and actual exception, or maybe do some logging, whatever. It's normal to catch and re-raise. That's pretty cool. Why shouldn't why shouldn't everybody use look before you leap? It's got problems. For example, it duplicates work. Your The look before you leap approach would be if x equals 0, raise 0 division error, else return y divided by x. So the example I gave before. Why check it when Python is going to check it again for you anyway? I know machine cycles and microseconds don't cost much, but they're not entirely free. Moreover, all these checks obscure the clarity of your code. You have check something, raise if, check something, raise if. By the time you have finally come to doing the operation, the reader has stopped following. What is the purpose of all this piece of code? Checking if there are errors. It's like, no, it's actually to do a division, but before I do a division, I need to check. Come on. Moreover, if you need to check 17 things, it's easy to accidentally check only 16. And now, the time the 17th happen, you get an exception you are unprepared for, and boom, what will happen? Moreover, either in multi-threaded programs without proper check, but more commonly when you're interacting with the world, like the file system, things may change from when you check to when you actually operate. Let me give an example. Remember the same functionality you already had? The look before you leap operation say, hey, wait, let's not try to read a file that isn't there. Let's check if the file exists, and then we open it and return. Otherwise, we go the default. Well, you know what? Between the instant you check if it exists and the next instant, another program may have run and deleted it. It's out of your control. Your operating system is in charge. You cannot block every other program in the world from deleting that file. So this isn't just dubious. This is a very bad mistake in programming, any language. Unless you're writing a kernel and you have complete control and can block every other program in the world from running when it shouldn't. That's the only way to do it. Well, in V3, where you have a file not found error, but I've already shown the alternative. Now, easier to ask forgiveness than permission is not a panacea. You have to do it right. For example, I would like to call a attribute method with a certain name on an object, otherwise, if the attribute isn't there, give a default. The natural way may seem to be the first one, but it's wrong. Why is it wrong? Because the try is covering both the getAttr, which checks it, like tries to extract the attribute, the method, by that name, but also all the execution of the method. If the method has an error, whereby it causes an attribute error, that gets completely hidden because it's caught in the exception. Again, the else clause is your friend. Learn to use else. If your Python program have try except all of them without else, you're doing it wrong. I'm sure you will find opportunities. See, just try the getAttr. This will only very specifically pinpoint missing attribute, which is the one case where you want to return the default. Otherwise, without exception guard, it's time for you to execute the method. This is particularly crucial when you move to large programs, because you must be looking for all causes. I'm sorry I said errors here, so I should say exceptions, because I did start pointing out that not all exceptions are errors, but in terms in which there are errors, there could be bugs in your code, or unfortunately, other programs aren't perfect either. So the exception handling of those essentially helps you diagnose the bug, but then add a unit test so that the bug gets caught and fixed before you run. Similarly, for mismatches between what you think a library does and what it actually does, make sure to add integration tests. The core part that you cannot likely solve is invalid inputs to your code. Why can you solve it? Because they come from humans. If you can re-engineer humans version 2.0, then that'd be great. But as long as we're stuck with the 1.0 beta, we'll have to make do. And so that's a great use for try except. Remember, let Python do most checks. I've already explained, Python checks a lot of prereqs, don't duplicate those. The same goes for an invalid environment. So it's not technically an input, but maybe there's a configuration file that somebody's supposed to have edited and it's somehow broken or so on. It's kind of like a bad input, so you should treat it the same way. The crucial thing to remember, the information you need as a programmer to fix diagnose and fix a problem is not the same information your end user needs. I cannot believe in the year 2016, once in a while you go to an otherwise decent site, there's some problem, and you're shown a traceback. Usually a Java traceback, but it's not as if it was a Python traceback, it would be much better. It would be just as useless and angry-making for me as a user. I can't do anything about it. What are these 500 lines of traceback for? For programmer laziness. So what the programmer should do, what I hope you all will do, is don't show the user a traceback. Design user error messages with care. Focus on what can they do now. Like if it was an invalid input, well, maybe they can just fix the input and go on. Definitely don't want a traceback. But if it's not something they can fix, apologize, ask them to try again, that kind of thing. So be focused on action. Make sure to save all that info somewhere. Maybe send it to yourself, possibly asking the user permission. Can I please send all the state that may contain private information? But, I also recommend, if you're on there, okay, can I now clean things up and restart the same process, like continue the same process, or should I kill that one and restart? I strongly recommend in general principle to go with restart, because it's so easy that obviously, if the error is complicated enough, you're not sure what happened. So it's really hard to make sure all the state of your program and libraries is back to new, except by restarting from scratch. Ideally, a little program on one side, watching things and dealing with the restart is more robust because your program itself is broken. So it might not restart properly. By restart, I mean exec, like new process, just, okay. I wish I had time to do justice to logging, because the normal reaction by most programmers when they start looking at logging is, oh my God, this is like more than all the rest of the language put together. Not quite, but that kind of like the impression you get. Why is it so rich? Because log is really, really your friend. To be honest, I've trimmed the coverage in the nutshell because the coverage in the online docs is superb and it's very big. So I'm trying to keep the nutshell down differently from myself. Anyway, the core idea that I want to give that's not anywhere in the things, make sure your logs are machine parsable. Yes, you will be sometimes reading them yourself, but more often than not, you want scripts, very well-designed scripts that process them and tell you what's good, what's bad. Because I strongly recommend, when in doubt, default to logging information. You may think, oh, I could save 2 bytes here and 1/2 a millisecond there, and then the first time you're trying to diagnose a bug in a server program from insufficient logs, you will see why I recommend, well, I'm not sure, then log it. You're not sure? Log it. Besides, don't log just errors. If you have the logs, the logging info logs from successful operations, that's a baseline, and you can have your scripts check for differences with a breaking case. That's much easier for you to find, oh, that's that was a problem, that if you didn't have the non-error case. Last slide before Q&A. If you want to forget one Python statement, I would recommend forgetting assert. Now, forgetting might be a bit of an overreaction, but the point is, it's so attractive. Oh, I just need to assert x greater than 0, and that will make sure the input x or argument x makes sense. It's not, because once your program is stable and you run it with -o in the normal optimized way, assert becomes a no operation. Yet, you have the impression that it's checking the sanity of your inputs and arguments, and it's not anymore. It's just there as unreadable docs. But it's not doing anything, and the fact that your program is debugged doesn't mean your user is debugged. He's still, remember, the 1.0 beta version of human, so he will do invalid inputs. Moreover, it's kind of a type of look before you leap, so it duplicates checks Python already performs. So use it only while you're developing and debugging for sanity checks, and leave it there because, hey, it's not really executable. It's kind of sort of docs, and if you have very thorough documentation strings, I congratulate you, but most of us tend to skimp doc strings and comments, so at least there's the asserts, which is kind of a comment. It becomes a comment because optimization removes it. But don't rely on its functionality beyond your debug. And here we are, the two important URLs, the PDF of this, the 50% discount on the early edition of Python in a nutshell, and we have 9 minutes. Sorry, I should have kept 10.
Thanks. Are there any questions?
A minor point about the -o option. I don't remember ever seeing anyone nor using it myself. Is it really used by anyone in production?
I would be astonished if somebody ran production programs with a 10% overhead of memory. Unless maybe your job is manufacturing memory, then the more is wasted, the happier you are. Why would your production programs carry along all the doc strings and kind of...
Other questions?
Hello. So you say that look before you leap is a bad approach. How do you cope with errors that you can show to the user? Because usually if you check before doing something, you can produce an error which can be translated to the user and the user can understand. On the other side, when you just catch an exception from Python, it's very hard to make sense from it and tell something to the user.
I don't see any difference in difficulty where, if not OSPath exists, the file, show beautiful error, versus try with open file, blah, blah, except file not found error, show error. It's exactly identical. Where's the difference? You get the same information either by the look before you leap, oh, does the file exist, or noting the file doesn't exist because you get a file not found error. That's a simple example, but there isn't much else. If you have something like a complex expression, you can analyze it post facto, I guess. If I don't think the user should be subject to complicated, convoluted version. If you can't explain to to the user the constraints on input, such this number must be greater than 0 or something like that, then there's some, I mean, yeah, you must enter 3 numbers such as they can form a triangle is already the sides of the triangle, I think, is already a bit complicated demand to make on a user. Maybe you should rethink your input, if that's what the kind of thing you mean. But many errors are actually between, so the user specify a file name and the file name isn't there. So it's not something you can check except by actually looking at the file system, and Python's going to look at the file system anyway on your behalf exactly the same way, actually a bit faster. So there isn't any royal road that you can get by checking, and Python can't.
One last question.
What do you think about the practice of passing an exception as an argument to an exception that wraps it, as opposed to using raise from, as you've shown in your talk?
I was a strong believer in the practice you mentioned in V2 because I had to. Indeed, if you look at the section of chapter 5 on custom exceptions, that's the example I give, because not just custom in terms of being a slightly different type, but custom in terms of having a little extra functionality. It was exactly the wrapping, which I missed from. Now that it is in Python version 3, I forget what version it was introduced in, 3.3 or 3.4, but anyway, we're only documenting 3.5. So I could imagine you preferring to assign dunder context or dunder calls directly and maybe have both. I'm not sure I've ever done it, anything except the built-in stuff, but maybe just because I haven't yet had that much experience working in Python 3.5, because most of my work is still in 2.7. But it is a good practice if you need it. Point is, you may not need it in V3.
Okay, thanks.